Yo, it's your boy Algebra coming to you live and direct from the studio, aka my living room. Time is about 9 p.m. and I'm gonna go ahead and kick it off with a little bit of conversation about hyperbolas today. Hyperbola is going to be our fourth conic section of the week. We started off by talking about parabolas and being able to turn them sideways now. We talked about circles. We talked about ellipses. Now we're going to talk about a hyperbola. So the idea is basically this, that you have those two cones stacked up on top of each other, pointing at each other, and this would be a line that is cut straight down through both of them. It's going to result in a figure that has a shape that is broken in the middle, where you could have a somewhat of a parabola going up, but also one that is pointing downwards at the same time. There's going to be a space in the middle, some special properties that take place within this hyperbola, but the basic idea is that they are symmetric, and we're still looking at having a center, the A, B, and C relationship, and trying to develop this thing from the same type of squared X and squared Y values. Having said that, just like every other conic section, you might have it where it's stacked up on top of each other, but you could always turn your paper sideways and be looking at a parabola that is horizontally major. Recap kind of how we did with ellipses earlier this week. This would be Y major. This would be X major. Either way we choose to look at it, there's going to be some special properties, and it's going to come from a formula. One of the first special properties I want to talk to you about right now is that in between the two pieces of this hyperbola, there are some asymptotes. The first asymptote looks like this. The second one goes across. The idea is that with these two asymptotes, your line is going to get really close, but it's never going to be able to touch. That's going to be a huge piece of information that we use today. Similarly, because we have these asymptotes cutting through the middle, we need to be able to place those. And that's where our A, B, and C relationship is going to come in handy. Inside of the empty space between here, it's kind of a box that's formed. And the asymptotes connect the different corners. These are the diagonal lines that would connect the edges of a rectangle. So our goal right now is to be able to identify this center point right here and take that center point, generate a box, and then fill in the hyperbola in the appropriate direction. It's going to be a formula that we use to generate these hyperbola. X minus h squared over a squared minus y minus k squared over b squared equals 1. So the main difference that you're seeing between a hyperbola and an ellipse right now is in the minus. This minus tells me that it has to be a hyperbola. Second piece of information. We always looked at which one was bigger on the bottom to figure out whether the ellipse was Y major or X major. Now all we have to do is look at the first one. If we start off with X and A, this means that it's X major. So in order to form a Y major hyperbola, we would have to flip this and make it say y minus k squared over b squared minus the x's and the a's. It's because this is first. So now we have a basic idea, a basic formula for how this hyperbola is going to work. Let's go ahead and take a look at a couple of examples. First example, I'm looking at x squared over 9 minus y squared over 16 equals 1. Notice the 1 is still the same as it was in an ellipse. Still have fractions. The big difference between an ellipse and a hyperbola is that now we're talking about subtraction. So for subtraction, first thing I want to do is identify what the center is. The center of this one is 0, 0. In the x direction, what I'm going to use this 9 for is to help create the box. The square root of 9 is 3. So I'm moving to the side 3 places. Let me move into the side in the opposite direction. Again, 3 places. There's going to be the sides of my box. Similarly, in the vertical direction, I'm going to be going up and down 4. This distance here is 4. Up and down again is 4. This is the top and the bottom of the box. So then the next question becomes, well, how do I know where to put the points? What about that asymptote thing that you were talking about before? What this box does is in the center of the box, you have that center of the parabola. We know it's going to be symmetric on either side. We know that it is an X major hyperbola, which means the vertex is going to be right on the edge of that box. 3 places away from the center this time. Okay then, Mr. Somerville, how do you know the width of the hyperbola that I'm supposed to be drawing then? What I want you to do is I want you to remember back to when we talked about rational functions. That was the 1 over x graph. It had an asymptote in the graph. And the asymptote said my line is going to be infinitely close to this asymptote, but not actually touch. So if I connect the 2 corners of the box, like this, and go the other direction, I'm going to kind of form a net for me to make sure that I stay away from. Notice it went through the center. It's connecting, it's using that 9 and the 4, or the 16. I have vertices, so by connecting here, I can generate the width of the hyperbola in question. So again, the big idea is that we are looking at placing the center, creating a box, using asymptotes to make a set of boundaries, and then generating the shape from there. Let's try this other one. Again, the center is at 0, 0. Why? Because there's nothing extra happening up here in this area. There's nothing going on inside of parentheses with an X or a Y. So I'll place that center at 0, 0. From there, I'm going to go sideways 5. That is in the positive and the negative direction. Going up and down 7 this time. Why is it 7? It's got to be 7 because that's the square root of 49. I can create a box using this information. By connecting the diagonals of this box, I create a net in which my hyperbola will sit. the vertex of the hyperbola itself is directly connected to the box in the x direction, and it is drawn thusly. First half, second half. There we go. So I'm going to go ahead and add in a couple extra pieces of vocabulary for you. Going sideways in this particular problem, we said earlier that this would be an X major. The major axis in a hyperbola is also called the transverse axis. Let's think back to geometry for a minute. You're talking about parallel lines and there was a line that went straight through it. We call that a transversal because it's going across all of the lines that you had. This is a transverse axis because it is going across the actual hyperbola. The transverse axis for this particular problem is this one. So if there's a transverse axis and it has a very sophisticated name, we should also be able to talk about the minor axis. This would have been a Y minor. Let me take you back one more time. Thinking back to how we were solving radicals and simplifying problems where you had a radical or an I in the denominator where it was working against you. It was that negative space where you didn't want to be. It was like the upside down world in Stranger Things. You don't really want to be there. We use the conjugate to get rid of that. So the space, the axis that you're trying not to use this time, we call it the conjugate axis. In this particular problem, the conjugate axis is going up and down. Is it possible to make that switch? Absolutely. All we would have to do is say that it's an X major, or it's a Y major hyperbola instead. We would just have to put the Y squared in the front of the problem instead of the X squared. And if we do that, it's not the end of the world. We just need to make sure that we understand now we're looking at something that is vertically dominant versus horizontally. Let's continue on this hyperbola journey in the second video in this sequence. You've been rocking with your boy Algebra. We're going on to the next side.